This presentation will demonstrate how to conduct a chi-square test in SPSS using an example study. The purpose of the example study is to test a new treatment for shoulder injury. The alternative hypothesis, or what we believe will happen, is that a greater proportion of subjects in the treatment group will have normal range of motion after 12 weeks compared to the control group. The null hypothesis is that the proportion of subjects with normal range of motion after 12 weeks will be the same in the treatment and control groups. The independent variable is nominal and has two categories, the treatment group and the control group. The dependent variable is also nominal with two categories, normal and abnormal range of motion.
Unlike other non-parametric tests like Mann-Whitney U-test or Kruskal-Wallis, the chi-square test does not have an analogous parametric test. A chi-square test is used when a researcher wants to test the association between two nominal variables, and it essentially tells us whether the value on one variable is contingent on the value of the other variable. It's a very common statistical test in medicine and healthcare, so it's important to understand how the chi-square test works and how to interpret the results.
This is an example of a contingency table summarizing the association between study group and normal range of motion. This type of table can help us determine whether having normal range of motion at the end of the study is contingent on receiving the treatment or the control therapy. There were 100 subjects in each study group, so 200 total subjects in the study. In this example, the proportion of subjects with normal range of motion at the end of the study is equal in the treatment and control group. The formula for a chi-square is shown at the bottom of this slide. The calculation involves finding the difference between the frequencies we observed in our sample and the frequencies we would expect if the null hypothesis were true. Recall that the null hypothesis is that there is no contingency between the variables. The expected count for each cell is equal to that cell's row total times that cell's column total divided by the grand total. For example, for cell A, the expected frequency is 100 times 100 divided by 200, or 50. In this example contingency table, all the expected cell counts under the null hypothesis are the same as the counts that we observed in our study. Therefore, our observations in the study are consistent with the expectation under the null hypothesis, and our alternative hypothesis is not supported. These data would result in a chi-square value of 0, which would not be statistically significant. Now, let's take a look at a more realistic example using the SPSS program. This is the SPSS data file. The study group status is here, and the range of motion status after 12 weeks is here. To run the chi-square, I click on Analyze, Descriptive Statistics, Crosstabs. Conventionally, the rows contain the independent variable, which in this case is the group status. Conventionally, the columns contain the outcome or the dependent variable, which in this case is the range of motion status. I'm going to ask SPSS to report the row percentages, which will help me in interpreting the results. I also will ask SPSS to give me the chi-square results. I click OK, and these are the results. We can see the contingency table here. We had a total of 57 subjects in the treatment group and a total of 50 in the control group. Among those in the treatment group, 40% had a normal range of motion after 12 weeks. Among those in the control group, only 12% had a normal range of motion after 12 weeks. We can already see that there's quite a large difference here in the percentages. If we scroll down, we can see the chi-square tests. We're going to look for the two-sided significance, or p-value. We can see that the Pearson chi-square value is 10.8, and the p-value, or significance, associated with that is 0.001. This value is less than the threshold that we typically set of 0.05. This means that we would reject the null hypothesis that these two variables are not associated. These findings provide support for our alternative hypothesis that a greater proportion of those in the treatment group will have normal range of motion at the end of the study compared to those in the control group.